Today's lesson, in section 4.6b, we'll be modeling with exponential and logarithm functions. So we have one more exponential function that I'd like to talk about, and then we'll talk about some logarithm functions that we can use to model certain situations. So here, Newton's law of cooling deals with if you have some object that's super hot and the surrounding area is not so hot, then as you, depending on the difference of the two temperatures and the rate at which it cools, then you get a exponential function that models the situation. So let d sub 0 be the initial temperature difference between an object and its surroundings, and if its surroundings have a temperature of T sub s, then the temperature of an object at time t can be modeled as T of t, so capital T of little t, will equal T sub s plus d sub 0 times e to the negative kt power. So k is a positive constant that depends on the type of object that you're talking about. So based on those properties, it could have a different value for each object that cools. So example 4 is talking about a cup of coffee has a temperature of 210 degrees Fahrenheit and is placed in a room that has a temperature of 85 degrees Fahrenheit. After 20 minutes, the temperature of the coffee is 140 degrees Fahrenheit. So find the temperature of the coffee after 25 minutes. So here, they're giving you enough information at the beginning to help you find that constant K, specifically made for the cooling of a cup of coffee. Okay, so they would give you different information if they were talking about like a dish that you had put in the stove to cook and how the rate at which that cools. So each object will have a different K value. So first I need to figure out my values. So for T sub s, that would be 85. Our difference will be 210, so the initial value that it starts at minus the surrounding, so it gives us 125. Also our t is 20 to begin with, and then capital T of 20, they say ends up being 140 degrees Fahrenheit. Okay, so using this information, I want to plug it in so I can find my K value. So 140 is equal to 85 plus 125 times e to the negative K times 20 power. So now I want to simplify and solve. So subtracting 85 to both sides gets me 55. And then I want to divide the 125 away, kind of like if I'm solving, so I can get rid of the base that's happening. So 55 divided by 125 gets me 0.44. So now, because I have a base of e, if I took both sides to the ln power, or to the log of ln, then my ln of e would go away, and I'm left with just negative 20k on the right. And so now you can divide both sides by negative 20. So k will equal a not repeating decimal. Okay, so I'm just going to write it down as 0.041. I'm not going to round it in my calculator because I want to be as exact as possible. So now once I have that, now I can go back so I want to plug in 25. So 85 plus 125 e to the negative 0.041 power times 25 up there. Okay, so now since I have this in my calculator, I want to multiply it out, so start by multiplying. And since your number is positive, just make 25 negative, just so you don't have to do an extra step. So I get negative 1.026, and then take e to that power. So I get 0.358, then times 125, gives me 44.79, and then add 85 to that. So the temperature of my coffee after 25 minutes should be 129.79 degrees Fahrenheit. Okay, so that should be my answer. So now let's move on to logarithmic scales. Now most of these scales you've probably heard of at one point or another, so you just probably haven't seen the formula that goes with them. So a pH scale is written as pH is equal to the negative log of H to a plus power. So that H plus means is the concentration of hydrogen ions measured in moles per liter, denoted as the letter M. Now, one thing to note is that for pH level, if it's greater than 7, then it's basic. pH, if it's less than 7, is acidic. So that'll be something that they ask you in your problems. Richter scale helps us measure the magnitude of earthquakes. So M is the magnitude, and that will equal log of I divided by S. So I is the intensity of the earthquake you're talking about, and S is the standard earthquake's intensity, which is measured as 1 micron, which is also equal to 10 to the negative 4th centimeters. Okay, and then also decibel scale is a measure of how intense sound can be, and that's used as B is the intensity level in decibels, which will equal 10 times log of I divided by I sub 0. This formula is very similar to the Richter scale one. So I is the intensity of the sound that you're talking about in watts per square meter. And then you have an initial one so it's a reference intensity, which is 10 to the negative 12th watts per meter squared. This is representing barely audible sound. Okay, so it's just like barely even whispering, so you can barely hear it. Okay, so example 5 says the hydrogen ion concentration of a sample of human blood was measured to be 3.16 times 10 to the negative 8 moles. Find the pH and then classify the blood as acidic or basic. So here, I want to plug this into my formula, capital H. So negative log will be a 3.16 times 10 to the negative 8th. Now, because our log is a common log, and we have a base of 10, this makes it pretty easy to plug in. So then, when I plug it in, that gets me a value of 7.5, roughly. So then, because it's 7.5, it's greater than 7, so that means it is a basic pH value, or level. Okay? Example 6 is measuring an earthquake in the United States, has an estimated magnitude of 3.7 on the Richter scale. In the same year, an earthquake in Ecuador was 4 times as intense. What was the magnitude of the Ecuador earthquake on the Richter scale? So first, let's use our formula to represent the other magnitude. So they don't tell us the intensity level of the one in the United States, but they do tell us this value from the scale. Now, using that, let's write a new equation or formula for the Ecuador one. Because it was 4 times as intense, then we would take 4 times I divided by S. So here I can also separate. And so, using expansion laws, because I also, now initially you see division, but I kind of want to make it so the log on the right has log of I over s, because we already know that that's equal to 3.7. So if I separate them by multiplication, there's multiplication right there, so 4 plus log of I divided by s, and that gives me log of 4 plus 3.7, because these two are equal to one another based on our last statement. Now I can plug in log of 4 in my calculator and add that to 3.7, and that gets me a value of 4.302, but for Richter scale values, they usually just round to the tenths place, so we'll go with 4.3 as our value. Okay. Example 7 says find the decibel intensity level of a jet engine during takeoff if the intensity was measured at 10,000 watts per meter squared. So here, since we're talking about decibels, we'll use our B times 10 to the log over I in I sub 0. Now you know what I sub 0 is. Oops. It's 10 to the negative 12th. But they also tell you this one. So if I converted that into scientific notation, or rewrote it as a base of 10, because my initials already is a base of 10, it makes this a lot easier. So 10,000 would be 10 to the 4th. So let's insert that in for I. And so now you can use your exponent rules. So dividing like bases, you subtract the exponents. So here, so then I get 10 to the 4th minus a negative 12, which is double negative. Gives me 16. So then now, another nice thing is because they're all in bases of 10, this is also a base of 10, so just like ln of e goes away, here also log of 10, base 10, goes away. So now we remember there's a number in front, so it's multiplication that you're doing. It's also like if I did power property, I would move this forward and I would multiply it to the front. So it's the same operation that's going on there. So my decibel level will be 160 decibels for the intensity of that takeoff for the jet engine. Okay? Have fun.